Good, wonderful morning, all chemists out there. It is just a beautiful sunshiny day, and I wish I was out there instead of doing this. But you know what? Chemistry really just wins over everything. So let's jump back into the acids. Let's finish those up because we need to talk about the polyprotic acids. All right, what in the world is a polyprotic acid? Well, it's one that has more than one ionizable hydrogen. So the ones that you will be most familiar with is H2SO4 and H3PO4. Now, literally, they are just acids. They have multiple hydrogens that can come off. So they have different K values. So there is a K value for each hydrogen that can come off. And as we saw earlier, if you take one off, it turns into a negative charge. So the second one, when it comes off, has to turn into a negative 2 charge. So the Ka1 is always stronger than Ka2, which is always stronger than the Ka3. So for polyprotic weak acids, the anion is formed in one step, and then it produces another proton, and they become smaller with each successive. I'm going to jump over to the whiteboard. All right, polyprotics. We're going to do sulfuric acid. All right, so can you come up with the ionization equation for sulfuric acid? Why, sure. H2SO4. Now, here's the question. Should I rip off both of them at the same time? Or should I take it stepwise? And the answer is nature's not going to rip them off at the same time, unless there's something very odd going on. All right. So my ultimate question is, can you tell me the K value of ripping them both off at the same time? Well, sure, but I need to look at what each one does individually. So for sulfuric acid, the first proton that comes off, Ka1, and I am looking at, where's my reference sheet? So I do not have a number for sulfuric acid. So you know what? We're going to make this sulfurous acid. And guess what? Ha ha. Of course we don't have one for sulfuric acid because it's a strong acid. So we're going to make this sulfurous acid. All right, so for sulfurous acid, Ka1 is 1.3 times 10 to the minus 2. All right, now that's actually pretty close to 1. That is actually much stronger than the other ones that we've been playing with, but still considered a weak. All right, and then if I take hydrogen sulfate ion, it can lose a hydrogen and make the sulfate, and its Ka is 6.3 times 10 to the minus 8th. Significantly weaker, significantly weaker. All right, well, that's interesting. But if you want to know what it is for both of them coming off, we're just going to use those equilibrium rules. Now, remember, I call it the Hess's law. Hess's law is really for thermodynamics, but it's the same idea. So if you want to know what the K value is of this equation, look up the equations for all of the pieces, and then you can add those together and multiply the K values down. So what I mean is, let's add these together, and H2SO3, nobody cancels it out. All right, how about HSO4 minus? Yep, there's one on each side. And on the other side of the equilibrium, a proton plus a proton is 2 protons, and then nobody cancels out the sulfate. And is this the equation that I'm interested in? Okay, does it match? Exactly. The answer is yes. So then K is the product of those. All right. So we can mathematically figure that out because we have numbers. And where is my calculator? All right, so 1.3 to the negative 2 times 6.3 to the negative 8. This is 8.2 times 10 to the minus 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Ooh, 10. Double check that. 6.3, 1.3. That was so wrong in my calculator. And confirmed. All right, so how easy is it to rip off both protons at the same time? It has the magnitude of a negative 10. Okay, not very likely, not very likely. But you can figure out that answer for any of the polyprotics that you have Ka 1s, 2s, 3s, and 4s for. All right, well, why do we like the polyprotic acids? A lot of them in nature. So for instance, the buffered system in your body uses carbonic acid. In fact, we're going to clear this. And we're going to play with carbonic acid. And in our next chapter, we're going to be talking about buffers. So you'll recognize that as carbon dioxide dissolved in water. And the answer is why, yes, it is. All right. Is it going to just lose both protons? You cannot look up this K value because the ones that I give you, or the most common reference, is to come off stepwise. So let's figure it out. So H2CO3 will lose one proton and make the bicarbonate, and that's Ka1. And I'll look that up in a second. And then HCO3, the bicarbonate, would be called Ka2. And those numbers are, let's see, carbonic acid, 4.3 times 10 to the minus 7th. And Ka2 is 4.8 times 10 to the minus 11th. Now, if you'll notice, this number is clear in the negative 7s on that sulfurous acid. That was pretty strong for a weak acid. I know that sounds funny, but that was a pretty strong one. Here's more typical. Okay, so negative 7. But of course, it's even worse for the second one to come off because it would have to make a negative 2 charge. All right, let's add these things together. And the bicarbonate cancels out on both sides. 2 protons plus the carbonate ion. Is that the equation that I wanted? Does it match? Yes. So the K value for this is Ka1 times Ka2. That is 0.3 to the negative 7, 4.8 to the negative 11, 2 point, let me see, 2 sig figs. So K is equal to 2.1 times 10 to the minus 17th. Whoops, 17th. Ow, that definitely doesn't want to come off at the same time. Let me double check those numbers. Yep, 2.1 times 10 to the minus 17. All right, are we going to deal with polyprotic acids? Yes, they occur a lot in nature, and then when we do titrations, we'll see different unique particles, not particles, parts of a titration that will actually be of interest. It kind of makes a nifty graph. All right, go back And to our notes. All right, just go. Okay, so our polyprotic acids. It has more than one ionizable. So phosphoric acid would have Ka1, 2, and 3. Sulfuric acid, Ka1 and Ka2. Now, sulfuric technically is a strong acid, but the second proton coming off is not strong. The second one is not strong. So in its family, you have H2SO3 and H2CO3, and I guess I should probably put, okay, phosphorus acid. Those are the ones that you'll probably see in this particular class. This one does not have a Ka1 on your list, but all of the others have Ka1s, Ka2s, and Ka3s. All right, that was just a little blurb on polyprotics. And I do want to go to one more place. Where are you? Where are you? Where are you? Oh, the general chemistry reference sheets. I'm going to come back to this in the future, but I just wanted to give you an idea of, hey, what are some of the acids and bases out there in nature that you probably are familiar with? All right, concentrated sulfuric acid. Played with that in lab before. 22 molar, okay, 22 molar, and it has a pH of a negative 1.3. And remember, I told you that the pHs can go below 0, so they can be negative. So wow, concentrated sulfuric acid, woohoo, negative 1.3 pH. Concentrated hydrochloric acid, you've also played with that in lab, is a negative 1.1. Hence the reason I keep those in the hood in a sand bath, and we're just very careful with them. All right, 6 molar is a negative 0.78. 1 molar is a nice pH of 0. What? pH of 0? Okay, I know that sounds weird, but it can be 0. And 0.1 molar is a pH of 1. Now, just to give you a generic idea, when I think strong acids, as far as pH is concerned, anything with a pH of 2 or less, I would consider that fairly strong, fairly strong. For bases, a pH greater than or equal to 11, I would consider fairly strong. Remember, strength ultimately is based on identity and concentration, okay? Identity and concentration. So acid, base. Don't forget, strength is equal identity and concentration. Because you can have a strong acid, you can have sulfuric acid that is diluted so much that it doesn't really have a nifty pH. Would it technically be considered a strong acid? Yes, but would the pH look like a strong acid? Not necessarily. All right, battery acid, which is sulfuric acid, is a pH of around 1. Again, if you play with your batteries, please be careful because, yes, there is sulfuric acid in there. Your stomach acid is anywhere between 1 and 3, and so that is why it hurts so bad when you throw up. Ow, you are bathing your esophagus and your mouth with, pretty much concentrated sulfur or concentrated hydrochloric acid. I guess not perfectly concentrated, but somewhere between like 1 molar HCl. 1 molar HCl. Now, lemon juice, for those of you that love lemons, which I am in that category, I love to eat them, is somewhere between 2.2 and 2.4, which that's still fairly strong pH. That's a pretty strong pH. It will eat the enamel off of your teeth. Ow. Okay. All right. And too much information. When I was pregnant, boy, did I throw up all the time. And this is a problem for women who tend to get very sick during pregnancy because all of that acid tends to eat the enamel off your teeth, and then your teeth can, start to get cavities. So if you drink too many things that are acidic, or, if you get sick a lot to your stomach, that can be a bad thing because the pH is so low. All right, so lemon juice is, between 2.2 and 2.4. Vinegar, little bit less acidic, between 2.4 and 3.4. Oh my, look at this. Soda pop. Soda pop is as acidic as vinegar. And guess what's in your soda pop? Phosphoric acid. Boy, you can use soda pop to clean a lot of things. So if you ever want to, get some stains off PVC pipe, throw it in some Coke or some Pepsi. That usually works really well. All right, apples are around 3. Carbonated water, which is, basically soda pop, is 3.9. Ooh, tomatoes, 4.5. All right, now those are still pretty acidic. And so for those of you that have made homemade salsa, when you are cutting up the tomatoes and things, yes, it really starts to irritate your skin. And when it starts to burn, it's literally an acid burn because tomatoes are quite acidic. But the salsa is definitely worth it. Just wear gloves or something, or wash often. All right, wine and beer. What? Clear down in the 4s to the 4.5s. Coffee is around 5. Normal rain, okay, normal rain is somewhere between 4.5 and 5.6. So you've heard the term acid rain. Well, most rain is slightly acidic. Acid rain is even more acidic than that. So for some of you, when you're out in the rain and it hits your skin, it stings a little bit. So if you don't have that nice protective layer, if your skin is dry, you can actually feel the acid in the rain, and it kind of hurts. All right, let's see. Ooh, milk. What? Milk is acidic? Insane. And the answer is yeah. So that old wives' tale, hey, if you have an upset stomach, drink milk. Well, you're adding acid to acid, by the way. And then also it'll curdle. So maybe not the best thing on an upset stomach, but it does have a lot of fat, so it tends to coat your stomach. So if that's the problem, milk would help. But if it's because your stomach, has too much acid, well, you're kind of pouring fire on fire there. Cheese, I made it so I can't see it. Our wonderful cheese. What? Cheese is also acidic? Look at this, 4.8. Boy, could we go into a whole conversation about cheeses, but it also falls into the acidic region. Okay, human urine, look at this range, 4.8 to 8.4. So it'll go all the way from acidic to basic, and it just depends on your specific physiology. So are you supposed to have acidic urine? Are you not supposed to? It just depends on a lot of factors, but just know that it's interesting that it will go in both realms. Human saliva is somewhere between 6.5 and 7.5. Drinking water can vary greatly, and so somewhere between 5.5 and 8. And you can definitely feel the difference. The water in Idaho Falls tends to be very, very alkaline, very alkaline. We'll actually test that in lab. Okay, pure water, of course, is a perfect pH of 7. Seawater goes into the basic realm, 7 to 8.3. Human blood, okay, very specific. It can't change the pH by very much, and it's 7.4. Baking soda, 8.4. Most of your detergents Okay, these are why they kind of feel itchy and burny to your skin because they're very basic at a pH of 10. Milk of magnesia, about 10.5, ammonia, 11.9. So most household cleaners fall into the basic region. And they're getting fairly strong. They're getting fairly strong. Let me see, bleach 12.5, calcium hydroxide 12.4. All right, now let's get into the strong base, sodium hydroxide. So lye is 13.1 molar, sodium hydroxide is 13, 1 molar is 14, and then 6 molar and 12 molar. Whoa. Yes, you can get above 14, and that is getting pretty basic. So again, are you going to memorize those numbers? No, but I thought it very interesting to point out just what you've seen pH as far as the world is concerned. So, take home messages. If you want to know how strong an acid is, ultimately you have to look at its identity and its concentration, and there's a lot of things out there that are easily tested. And so in lab, we're going to play with that. We're going to use some pH paper, we're going to use some indicators, and we're going to use some pH meters to just play around and see what kind of pHs there are. And we will test the pH of our water here in Idaho Falls. All right, until next time, Jolly out.